All right, so this is section 6.4. And we just heard a little thing from Dave Ross about election day and polling, etc. Now, did anyone get called last fall? Asked you how you're going to vote or if you're going to vote? You did? Really? Oh, that's cool.
Oh, yeah, I received several calls.
Yeah? Okay. When I don't recognize a number, it just goes right to voicemail for me. I don't answer it usually. So I didn't get polled, but somehow or another there was a lot of polling going on. And let's try and understand why that is and what the objective is. And it's going to really bring into play some of our vocabulary here. Now we're going to start out with our population. Our population is what you define it to be, what you're studying, what you're interested in. And in this case, let's assume that our population is registered voters. But it's whatever you define it to be. Now, what you'd like to know from registered voters is who they're going to vote for. So, who are you voting for? The percentage of people that are going to vote for one candidate as opposed to the percentage that are going to vote for the other candidate, and then there's a small percentage that are undefined. But when you calculate these percentages from the population, you get what's called a parameter. A parameter is a numerical value that characterizes something about a population. But it's difficult to know that. So instead, what we do is we take a small subset of that. We take a sample. And then we calculate, from there, we calculate sample statistics. Now what we're hoping is that these sample statistics are good estimators of the population parameter. A lot of times it's very difficult to actually know something about the population parameter other than through some kind of statistical estimate. But let's review things a little bit. These are our sample statistics, and these are what they estimate. So what's X bar represent? That's the mean. And in this case, it's the sample mean. How about S squared? Variance. And then the standard deviation. And then a new one. P hat is what I'll call it. This is a sample proportion. So if you're trying to find out, what percentage of the voters are going to vote one way or another, then you're finding a proportion. Now these are sample statistics, and what we're hoping is that they're good estimates of the population parameters. That is, the mean is a good estimate of mu, the population mean, or that S squared is a good estimate of the population variance. S is a good estimate of sigma, population standard deviation. And finally, that P hat is a good estimate of P, the population proportion. Now, they may not be perfect estimates, but we're hoping that they're good estimates. And we're going to try and see what we can do to improve the quality and kind of get a handle on the quality of these estimates. So, let's take an artificially small example, and for that, I want to go to our second handout. So like I said, this is artificially small, but I want to draw a lot of conclusions out of this. We're going to look at the heights of the starting five of a basketball team. So it's these 5 heights. Now, suppose that you're really, really lazy, and instead of trying to find, parameters out of this, that is, find the average of all these or the standard deviation of all these, you're just going to work with a sample of these. You're like, what, I don't want to count all of them and add them all up, etc. We're just going to work with a sample. So my first question to us here today would be, all right, well, how many different ways can I take a sample of size 2 from this? And that's right here. 5 choose 2. You remember how to calculate that? How would you calculate 5 choose 2? Remember that from your calculator? So, well, let's type it. Let's grab a different one. So type in the number 5 first. I guess you don't have to, but I will. Go over to the probability menu off of the math menu. Then the third option down gives you combinations. There's 10 different ways I can choose a sample of size 2 from a population of size 5. So 10 here. And here's those samples. Here's all the different 10 ways you can choose 2 people from that team. Okay. Well, then what? Let's take a look at the sample range. So the sample range, what is the range? Remember? Yeah, the max minus the min. So in this case, it's just the difference of these two. So that'd be a 2 here, a 3 here, a 5, a 10, a 1, 3, 8, 2, 7, and 5. So those are all the different possible sample ranges. Now if I add those up, I'll get a total of 46. Now when you sample, you don't always expect to get the population parameter. And let's determine that for ourselves here. What's the range of this data set? So the range would be 10, right? 76 from 86 gives you a difference of 10. So that's the population range. How did our estimates do? Were our estimates pretty good for samples of size 2? Not really. And we hit it once, but only once. Now, if I've got 10 of these values, what was the average estimate here? Can anyone tell me? What's the average sample range? 4.6. Just divide that by 10, which means moving the decimal, 4.6. Not so good. What if we increase our sample size? 5 choose 3, that's kind of symmetric with 5 choose 2. Rather than which 2 you're going to choose, you can think of which 3 got left out here. Same kind of thing. You're still going to get 10. So I've calculated the sample range for us here. What's the average of our sample range for samples of size 3? Yeah, 6.9. It's still not all that good, is it? So you could go up to the last one as well. Find the sample range on this last one. And I think it's going to be a little bit better because our sample is almost the entire population. So let's see, that'd be 5, 10, 10, 10, and 8 for a total of 43. This time we get an average of 8.6. But none of these are really good estimates. So that's kind of a bummer. The sample range is not a good estimate of the population range. And I'll talk about that a little bit more in a minute. Let's look at the mean, the sample mean, and see how that does. So for all these samples of size 2, here are your various sample means. If I add up all these, what's the average sample mean? 80. 80. And now by coincidence, if you actually calculated the population mean here, so for that I'll use mu, the population mean is also 80. So that's nice. At least what this is saying is that on average, the sample mean, now sometimes it's higher, sometimes it's lower, and in one case we got it right on, but on average, at least this equals the population mean. So sometimes you're higher, sometimes you're lower, but overall, on average, you'll be right on. And that's what we want. We want something that's a good estimate of our population parameter. This is our sample statistic. This is our population parameter. On average, we're doing okay here. What if we play that game for samples of size 3? Again, I've calculated all the sample means for you. This total should have been over here, 800. What's the mean of these sample means? 80. And likewise for samples of size 4, this total is 400. Divide 400 by 5 and you get 80. Wow. So what's that saying? It says a sample mean is a good estimate of your population mean. On average, if you look at all the different possibilities, on average, your sample mean will give you the population mean. So that's a good quality from a statistic, and that makes this thing an unbiased estimator. So let's go back to our other handout. You've got an estimator, which typically is your sample statistic. That's used to try and give you a guess as to what the population parameter is. That's what this diagram is all about. But it's an unbiased estimator if, on average, it gives you what you're looking for. Now, on average, when we're dealing with the sample range, on average, it didn't give me what I was looking for. It did maybe once or twice. But on average, it's not giving me the sample range. In contrast, on average, the mean gives me the population mean. Population mean was 80. The average of my sample means is 80. So that makes the mean an unbiased estimator. Now, here's a short list of some of the parameters, some of the statistics that we can use in this course. These are your unbiased estimators. These are your biased estimators. We've already seen 2 of these. The range, that didn't do so good. The range was a biased estimate. The sample range was a biased estimate of the population range. But the mean is an unbiased estimator. Know these. Know which estimators are biased and which of them are unbiased. Now, the one that's a little bit annoying is the standard deviation. Standard deviation is actually a biased estimator of the population standard deviation. Except the bias isn't too bad for large samples. It's relatively small, so we'll use it anyways. But typically we don't use the sample medians and sample range to make estimates of those parameters. They're biased estimators. Let's go back to handout 2. On the bottom row of this diagram is my original population, so I can call that a sample of size 1. And then up here, I've got a sample of size 4. I've graphed that for us. Let's graph some of our other estimators for samples of size 2, samples of size 3, etc. So what I'm going to do for samples of size 2 is I'm going to plot these different possible estimates. And let's just see what happens as you increase the sample size. So earlier in the book, something like this would have been called a dot plot. We're going to do a dot plot for our current set of data here, which is this distribution of sample means. So the first one is 77. So I'll put a little dot there. Then I've got one at 77.5. There's one at 78.5. There's one at 79.5. There's one at 80. There's one at 81. I've got one at 82. One at 82.5. And one at 83.5. So that's for samples of size 3 or 2. Let's see what happens for samples of size 3. So for samples of size 3, I've got 77 2/3 about here, 78 1/3, 78 2/3, 79 1/3. I've got one spot on at 80, 80 1/3, 81, and then another one at 81, so I'll put the dots stacked. 81 2/3, and 82. Now, there's a little trend here as you increase the sample size. Keep in mind what we're looking for, what we're trying to do with these samples is estimate the population mean. So the population mean is right here. Mu equals 80. So what's happening as your sample size increases? What's happening to all these different possible sample means? Can you describe any trend here? Yeah, they're getting closer to 80. Getting closer to 80. On average, if you averaged any of the values in any of these rows, you're going to get 80. So the sample mean is an unbiased estimator. On average, it gives you what you're looking for. And somebody said that you're getting closer to 80. Yeah. What's a way we can describe the fact that we're getting closer to this central value? What word do we have in statistics that describes how spread out the data is? Range, okay. Range, what else do we use to describe? Variance, yeah. The variance or the standard deviation of these things is decreasing. So as you increase your sample size, what's happening? Are you more likely to get a good estimate of the population mean? Absolutely. Because even in the worst case, let's say we had a sample size 4, even in the worst case, you're not going to be off by that much. In the worst case, you're going to be off by 1.5. But in the best case, you're going to be off by like 1/4. So what conclusions should we draw from all this? Well, I'm glad you asked. Let me help you. The big one, the absolute biggie, is that the sample mean is a random variable. X bar is a random variable. If you take a different sample, you're going to get most likely different sample values. So that the sample mean itself is a random variable. How about the next one down? the mean of the random variable x bar is the same as the blank mean mu. What should I put in here? Population. That's good because that makes this an unbiased estimator. As the sample size increases, the blank of the random variable decreases. What can I put in here? Variance or standard deviation. So either one. Standard deviation. So as you increase the sample size, standard deviation of x bar decreases. And we can see that. There's a nice visual representation of that right here. As you increase the sample size from 1 to 2 to 3 to 4, look what's happening. These values are getting closer and closer together, which necessarily means that their standard deviation is getting smaller. Okay. There's one last thing that I want to mention / look at from this section. It's not something we've gone over very much, but I'm going to go over it now. S squared was our sample variance. It was calculated by summing up the data, summing up the squared deviations of the data. So x minus the sample mean squared, and then dividing it. And then instead of getting the average by dividing by n, the average squared deviation, we divide by n minus 1. It's not a feature that I've really talked about a lot in this class, but we're in the position to talk about it now. In comparison, sigma squared, which is our population variance, is calculated this way. Sum of your data minus its mean. But when we're dealing with populations, I no longer use x bar. What should I use here? Mu. Good job. And then instead of a sample, the count for our sample, n, small n, we use capital N. We're going to divide by n. What's one striking difference that you notice in these two formulas? Yeah, the minus 1. So here you're dividing by n minus 1, as opposed to here you're dividing by n. Now the reason for this is that makes S squared an unbiased estimator. So that's a good thing, because on average, the sample variance is going to give you the population variance when you divide by n minus 1. And I'm not going to go into a detailed discussion about that any further. It's just dividing by n minus 1 makes this an unbiased estimator. So dividing by n minus 1 in the above formula makes S squared an unbiased estimator. When you look at output from statistical programs, a lot of times you'll see two different calculations. You'll see one for the sample standard deviation and one for the population standard deviation. The sample standard deviation would be simply the square root of this, square root of x minus x bar squared divided by n minus 1. And the population standard deviation would be the square root of this. But it's going to make a difference. Let me see if I can't call up some data. Yeah, here we go. So I happen to have some data in my graphing calculator. Let me just calculate this. Notice I get two values here. I get S sub x and sigma sub x. So the top one is your sample variance, and the bottom one is your population variance. So it's saying, okay, I'll let you decide. Is this sample data or is it population data? It's giving you both. The population standard deviation is always going to be smaller because you're dividing by a bigger number. You're dividing by n as opposed to n minus 1. So S is always going to be greater than or equal to sigma, always. The only case in which I guess they would equal would be if they're both 0. All right, let's kind of recap a little bit. We take samples because we want to try and find an estimate of a population parameter. Doesn't matter what you're looking for. You're looking for a mean, variance, standard deviation, proportion. When you sample from a population, you're calculating a statistic. And that statistic, we hope, is a good estimate of its population parameter. It's probably not going to be the exact thing, though. So you have to take that into account when viewing your statistic. On average, the sample mean is going to lead you to the right answer. May not in any particular case, but on average it'll do well. That makes it an unbiased estimator along with the variance and population proportion. Some of our estimators are going to be biased. On average, they're not going to work well. We worked with that with the range. So the range was a biased estimator. Bummer. Make sure you know which are biased and which are unbiased. Yes?
Standard deviation considered biased?
Standard deviation is a biased estimator. It's not horrible, but it is a biased estimator. Now, when you calculate a sample mean, the sample mean itself is going to be a random variable. You can see that here. Different samples have different values. Different sample means have different values. So the good thing, though, is that if you increase your sample size, the standard deviation of that random variable is going to decrease. You're more likely to get a good estimate of the true population mean, which of course here is 80, with a larger sample size as opposed to a smaller sample size. Notice with a smaller sample size you can get something as low as 77 or as high as 83.5. But up here, I mean, the worst you can do is 78.5. So you're getting pretty close with a larger sample size. As your sample size increases, the standard deviation decreases. So when people do national polls, a lot of times they can do a pretty good job with samples of size 1,000. And we'll see more and more of that as we move into Chapter 7. Any other questions regarding Section 6.4? Let me give you a few problems of homework to chew on. So for homework, one A and B, 3 and 5. All right, I know that's a lot. I know it's a lot. I know it's the holiday weekend, but all right, please don't get down on me too much for keeping you too busy. All right, that'll do it for Section 6.4.